We've talked about the idea of infinity before, the idea that negative infinity is not super tiny, it is large without bound, but in the negative direction along an axis, either the horizontal axis or the vertical axis. We've also talked about the fact that I never want to see you pick up the infinity symbol and perform any mathematics on it at all. That is a big no. I don't ever want to see that. The reason I'm bringing it up again at the beginning of this lesson is this is the first time that you're going to be highly tempted to do that. When we are evaluating limits that are infinite, you're going to want to pick up infinity and evaluate it. And I really don't want that to happen. For this lesson and next lesson, you're really going to be tempted to do that. So this is a reminder that infinity is not a value at all. We cannot pick it up like any other real number and add it, subtract it, or do any kind of mathematical operation on it at all. It doesn't represent a numerical value. It represents a mathematical idea of large without bound, meaning large with no measure. So when you see things like infinity over infinity, that does not equal 1. Why does it not equal 1? Because this infinity is not the same measure as that infinity. They don't have a measure. They don't have a value. They are not measurable. So with the idea of infinity, we'll never find the largest number lying along the real number line. So we can't say that things like infinity over infinity equal 1 or infinity minus infinity equals 0. We don't know this. This is not a true statement. So be very careful for this lesson and the next one that you're not tempted to pick up the infinity symbol and evaluate it like a number, and you're not tempted to say, well, because it's infinity, if I take infinity away from it, I'll get 0. Not a true statement. So now we're going to talk about the idea of infinite limits. There are infinite limits. In the next lesson, we're going to talk about limits at infinity. These are two very different ideas, so don't get them mixed up. The line x equals c will be a vertical asymptote of the graph of a function y equals f of x if any of the following four statements are true. If we approach an input value on our function f of x, either from the right or from the left, and we get the results of those, is that the output values are going either to positive infinity or negative infinity, that tells us graphically that as we approach c in the plane on a function f of x, let's look at approaching c from the right. As we approach c from the right, number 1 says our outputs are headed to positive infinity. If we approach c from the left, number 2 says our outputs are approaching negative infinity. That is the definition of a vertical asymptote. Now, not every vertical asymptote has to have just this going on. We have all kinds of behavior on functions as they travel along vertical asymptotes. As we approach c from the right and from the left, we may have both outputs going to positive infinity. We could have both outputs going to negative infinity. The example a while ago is from the right we were going to positive infinity, and from the left we were going to negative infinity. We could have the opposite going on. From the left we could be going to positive infinity, and from the right we could be going to negative infinity. That's why there are only these 4 rules, and when it comes right down to it, there's really only 2 rules. As we approach an input value from the left of a function, if we get positive or negative infinity, that tells us we have a vertical asymptote. If we approach an input value from the right of a function, and we get either positive or negative infinity as a result, Again, that tells us we have a vertical asymptote. We have been taught up to this point to identify vertical asymptotes of rational functions by looking at what's going on in the denominator and setting that denominator equal to 0 and finding the x values that might make that a true statement. Then we knew we had vertical asymptotes there. Well, actually, the first week that we started class, we learned maybe we don't have vertical asymptotes, maybe we have a hole. And we could use limits to identify where we had a hole as well. Now we can use calculus to identify when we have a vertical asymptote. And the power of using calculus is that the result of that limit not only tells us we have a vertical asymptote, but it tells us the exact behavior of our function along the asymptote. We know whether we're going to positive infinity or negative infinity. We know on which side of C we're exhibiting that behavior. So these limits tell us much more than even our algebra work that we brought with us to this class. We know exactly what the outputs of the function are doing near those input values where there's a vertical asymptote. So we're going to use infinite limits to explore vertical asymptotes. So here's a parent function, our parent reciprocal function. It has a vertical asymptote at x equals 0. We know we cannot put 0 into this function and get a well-defined output. We understand that the denominator equals 0 gives us a vertical asymptote. But what we didn't know using algebra was how the function behaved on either side of that input value where we had the vertical asymptote. Now we can explore what those outputs are doing. I want to talk to you about the idea of using tiny and huge as opposed to 0 and infinity. It helps us determine what the analytic result of our limit is. If the denominator is positive, then the fraction is positive. So as we approach positive input values, that's approaching 0 from the right, we are putting positive tiny, tiny, tiny values in this function for x. How tiny? Infinitely tiny. They're super, super small. So this would be 1 over positive tiny values. A tiny value would be 0.0000 with infinitely many zeros and then 0, 1. That is a super tiny number. If I take 1 and divide it by a really tiny number, and 100 million is not a tiny number, but there's 1/100 millionth, and that's 1 divided by 100 millionth. That's going to give me 100 million. That's a pretty big number. So if I'm super tiny, an infinitely tiny number, that's going to give me a huge output on that fraction. And that's where this comes from, because 1 over positive tiny gives me positive huge. Positive huge, in the idea of a limit, is positive infinity. So this tells me that as my input values approach 0 from the right, my output values are headed to positive infinity. That's what that result means. And the same thing here. If I put negative tiny values in this function, it's going to yield negative huge values as outputs. So as I approach 0 from the left, which are super tiny negative input values, my output values are approaching negative infinity. So not only have I verified that I have a vertical asymptote using calculus, I can tell you exactly how the outputs behave on either side of that x value that's giving us mathematical trouble. There's the power of infinite limits. Here's another function. This is the function 1 over x squared. And as we put in super tiny positive input values, we can see, as evidenced on this graph, that the output values head to positive infinity. And that's true analytically because 1 over positive tiny squared, if you square a positive tiny number, you get an even more tiny number. And so that leads us to positive huge. Makes sense. If we put a negative tiny number in this function, 1 over x squared, then negative times negative is positive. That's why we still have positive huge outputs as we have super tiny negative inputs. Since the left hand and right hand limits exist and are the same, the overall limit exists, and it must be infinity. So the overall limit exists on this function, but it did not exist on this function because the right-handed limit went to positive infinity and the left-handed limit went to negative infinity. Just because the limit exists, however, doesn't mean the function is continuous. So be very careful. So that finishes this lesson on infinite limits.